Richard Feynman, he wasn't just some Nobel Prize-winning physicist. He was an incredible teacher, a master at taking these huge, complicated ideas and just making them click. So here's the question. What did he think was the single most important idea in all of science? The one thing you absolutely had to know? Well, he boiled it all down to just one sentence. And that's exactly what we're going to unpack right now.
So to really get a grip on how science works, Feynman came up with this brilliant analogy. He said, look, just imagine the entire universe is like a giant game being played right in front of you.
Yeah, he called it a great chess game being played by the gods. And here's the thing, we're just the audience. We get to watch the pieces move around the board, but we have no idea what the rules are. We can't ask the players, all we can do is watch. And that's it. That perfectly captures the whole challenge of science, right? We see the effects, the moves on the board. And from that, it's on us to try and figure out the fundamental rules of the game.
So think about that for a second. If you can't see the players and you can't read the rule book, how in the world are we supposed to figure any of this out? It really frames the whole quest of science as this grand, amazing mystery that we're all trying to solve. Just one observation, one move at a time.
Okay, and this brings us right to his core idea. To really cut to the chase, Feynman set up this fantastic thought experiment.
Imagine this scenario he laid out. A global cataclysm happens. All of our scientific knowledge, every book, every discovery, poof, it's gone. And you get to pass on only one single sentence to the next generation. What sentence would you choose? What one idea contains the absolute most information in the fewest possible words to help them rebuild everything?
So what was his answer? Was it E equals mc squared? Some other complex equation? Nope. It was something so beautifully simple, yet unbelievably powerful. It was the atomic hypothesis.
All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another. Man, there's a staggering amount of information packed into that one little sentence. Let's break it down. You've really got three key ideas, right? First, atoms are real. They exist. Second, they are never, ever still. They're in constant, perpetual motion. And third, they're governed by these two competing forces, a gentle attraction that kind of pulls them together, and a really strong repulsion that shoves them apart when they get too close.
Okay, so that's the big idea. But how does it actually unlock the secrets of the world we see every day? Well, to put it to the test, let's go on a little journey. We're going to dive inside a single drop of water.
So, let's imagine we can magnify that tiny drop of water 1 billion times. What would we actually see? I mean, that scale is almost impossible to get your head around. But, of course, Feynman had a brilliant way of putting it into perspective.
He said, okay, imagine an apple. Now blow it up to the size of the entire planet Earth. The atoms inside that Earth-sized apple, they would only be about as big as the original apple you started with. That's the tiny, unbelievably crowded world we're about to step into.
Down here, at this scale, liquid water isn't this calm, smooth thing we see at all. No way. It's this teeming, chaotic crowd of H2O molecules, and they're all constantly jiggling, bouncing, and crashing into each other. So why does water stick together in a drop? Well, that's that gentle attraction from Feynman's sentence. They're all kind of stuck together, just enough to maintain a volume, but not so tightly that they hold a rigid shape. You know, figuring this out, it's like learning one of the very first rules of that great cosmic chess game.
Okay, so what happens if we crank up the heat? Well, that jiggling motion gets more and more frantic, more and more violent. And eventually, these molecules get so much energy that they literally break free from that gentle attraction holding them together. Boom! They fly apart, bouncing off the walls of whatever container they're in. And that constant bombardment against the walls, well, that's what we feel as pressure. And just like that, using our one sentence, we figured out another rule of the game. Add energy, and the pieces fly apart. All right, now let's go the other way. What if we cool the water down? That jiggling slows way down, until the molecules pretty much lock into place. They form this rigid, ordered pattern. And it's a beautiful pattern. It has this hexagonal symmetry, which is exactly why snowflakes always have 6 sides. And look, see those holes in the structure? That open pattern is the key. It makes ice less dense than water, which is why ice floats. So, liquid, gas, solid. 3 states of matter, 3 huge rules of the board, all explained by that one incredible sentence. So, here's the really crucial point. This atomic hypothesis, it doesn't just tell us what things are. It explains what they do.
It's all about the processes, the actions that shape our entire world. Let's take something like evaporation. At the surface of any liquid, you've got these molecules constantly jiggling around. Every once in a while, one of them gets an extra hard knock from its neighbors, like getting shoved in a mosh pit, and it gets just enough energy to break free and escape into the air. And here's the really cool part. Since it's the most energetic, fastest-moving molecules that are escaping, the average energy of all the ones left behind actually goes down.
And that, right there at the atomic level, is why evaporation is a cooling process. It's why you feel cold when you get out of a pool, and it's why blowing on your hot soup actually works. You're literally just clearing away that little cloud of high-energy escapees, making room for more of them to fly off and take their heat with them. It's not just an old wives' tale, it's physics.
You know, the same exact logic explains how things dissolve. Think about salt in water. There's this constant battle going on. Atoms are leaving the salt crystal and jumping into the water, while others are leaving the water and rejoining the crystal. If more atoms leave the crystal than come back, well, the salt dissolves. If more come back than leave, it crystallizes. And if the two rates are perfectly balanced, that's equilibrium. It's all just this frantic microscopic dance.
Okay, so let's zoom out, because now we get to the final and honestly the most profound implication of this single, powerful idea.
Feynman really took this idea to its ultimate conclusion. He asked if all of this, all the life of a stream of water, can be nothing but a pile of atoms, how much more is possible? And then he turns the question on us, on life itself. He asks if it's possible that that thing walking back and forth in front of you is a great glob of these atoms, with all the possibilities which you see before you in the mirror. I mean, think about that. From a simple drop of water to the complexity of human consciousness, it's all just atoms, arranged in more and more incredible ways.
You know, this one hypothesis has arguably been the most fruitful idea in the history of science. It unlocked chemistry, biology, physics, everything. But it also brings us right back to that great chess game. We've figured out an absolutely crucial rule of the game, that everything is made of these jiggling atoms. But the board is vast and the game is far from over. There's so much more to learn. And it leaves us with this incredible, lingering question. What new rules, what amazing discoveries are still out there waiting for us on what Feynman called this expanding frontier of ignorance?